there are three options for how to calculate this kind of main effect. The most straightforward one, in my opinion, is to fit a version of the regression model that simply does not have the interaction in it. In this version of the regression model, spots and fur simply are two main effects in the first place. And here we have a slope for spots that's negative 18.44, indicating that the dogs with spots ran the obstacle course 18 seconds faster than the dogs without spots, adjusting for whether their fur was curly or straight, but not estimating this slope at a specific value of curly versus straight. Another way that we can do it is to center the indicator variables. I can center the spots variable by just taking the original spots vector and subtracting its own mean. And notice that I'm not using na.rm equals t here because I already know that this dataset does not have missing values. If there were missing values, then I would need to make sure that I calculate this mean based only on those dogs that are going to be included in my regression model, and we'll come back to that later. But if you take a vector and subtract its own mean, then you get a centered version of that vector that has a mean of 0. This original vector spots was binary, it was just zeros and ones, but I can still subtract the mean. It just results in a vector of values that are slightly less than 0 and slightly greater than 0. I would like to do the same thing to the indicator variable for curly, so I'm going to create a numeric indicator variable for curly by testing which fur types are curly in the factor version of the fur variable, converting those trues and falses to numeric so that the trues will become 1 and the falses will become 0, and then assigning that to a new vector within the zoom data frame. And finally, I'm going to center the curly vector in the same way that I centered the spots vector. The result is that now I have two new binary vectors in the data frame, one called spots centered that has 115 dogs that are coded with the value negative 0.617, and 185 dogs that are coded with the value 0.383. And I have a vector curly centered that has 168 dogs coded with the value negative 0.44 and 132 coded with the value 0.56. These are still binary indicator variables, but now the reference point, the 0 point, lies somewhere in between the two categories that are actually present in the data. I can fit a regression model that has these two centered indicator variables as predictors. I'm just replacing spots with spots centered and the fur factor with curly centered in the model formula specification. And if you remember the information from the previous videos, you should realize that this regression model has the same fit as the other models with the interaction that we looked at a few moments ago, because all I've done is linear transformations to the two predictor variables that are included. And that means that the residuals are the same, the fitted values are the same. The slopes represent different information about the relationships between the predictor variables and the response variable, but the model fit is exactly the same. And now we've got key information about this model encoded in these slopes. So the slope for spots, for example, is negative 17.47. And because the moderating variable is centered so that 0 represents the mean of the curly indicator variable, negative 17.47 represents the estimated association between spots and time on the obstacle course at the average point of fur type. The slope for spots is estimated somewhat closer to the straight-furred dogs than to the curly-furred dogs, because it takes into account the fact that there are more straight-furred dogs in the sample. We can also do a contrast-coded version of this analysis. When I contrast code a variable, I can pick any positive value and its negative equivalent. I prefer using negative 0.5 and 0.5 because this version of contrast coding maintains the meaning of the slope, that is, the difference between the conditions. But using negative 1 and 1 is just as valid and more commonly used. In order to contrast code these two vectors, I want to create a version of the curly indicator variable where its values are just negative 0.5 and 0.5, and a version of the spots variable where its values are just negative 0.5 and 0.5. And that's very easy to do by taking the versions of them that have 1s and 0s and subtracting 0.5 from them. So the 0s will become negative 0.5 and the 1s will become 0.5. This table illustrates that the 168 dogs with straight fur are now coded as negative 0.5, and the 132 dogs with curly fur are coded as 0.5. I can fit a linear regression model that uses these contrast-coded versions of the indicator variables. The slope for spots is negative 18.13, indicating that the difference in obstacle course time for the dogs without spots and the dogs with spots was 18.13 seconds, at precisely the midpoint of curly and straight fur. This is like averaging together the effect of spots for the curly-furred dogs and the effect of spots for the straight-furred dogs without taking into account the fact that there were more straight-furred dogs in the sample. I realize that that is kind of confusing to think about when we're just looking at regression output, so I want to give you a graphical illustration of the three models that we just looked at with three different types of main effects in them. Here is a plot of the means of the various groups of dogs. So the dogs with straight fur and no spots are represented by this purple square, where their mean time on the obstacle course was somewhere around like 97 seconds. And the dogs with straight fur and spots are represented by this green circle. Their mean was around here, and so on. Here are the sample sizes for those four groups of dogs. This is key for this illustration because all three types of main effects will come out the same if all of the cell sizes are the same. So I purposely set up this example so that there would be wide discrepancies in the sample sizes of each of the four types of dogs. Given that there are 36 dogs that had no spots and straight fur and 132 that had spots and straight fur, there are 168 total dogs with straight fur. And that's critical for the type of main effect. That's like a weighted average based on the sample sizes of the moderating variable. There are 79 curly dogs with no spots and 53 curly-furred dogs with spots, resulting in 132 total curly-furred dogs. So there are more straight-furred dogs than curly-furred dogs in the sample. These lines represent the slopes of the curly variable in the regression model. Among the dogs with spots, the curly-furred dogs were somewhat faster on the obstacle course. Among the dogs with no spots, the curly-furred dogs were almost the same speed on the obstacle course as the straight-furred dogs. The vertical distance between these lines represents the slope for the spots variable in the model. So when straight was the reference category for fur type, the slope of spots was like negative 13. And when curly was the reference category, the slope of spots was something like negative 24. These blue lines indicate the magnitude of the difference between dogs with no spots and the dogs with spots at each of those two reference categories. In other words, those are the conditional slopes of the spots variable when the reference category for fur was straight or curly, when straight was 0 and when curly was 0. Those are the two simple effects that form the basis for our usual understanding of the interaction in this regression model. And I'm going to use them as reference points for understanding what the overall main effects mean. One type of main effect we might choose to estimate falls right in between these two conditional associations. This solid black line represents the contrast-coded version of the main effect, where it's a conditional association between spots and seconds at the point precisely between straight and curly, without regard to the sample size of straight or curly. So the distance from the conditional effect plotted on the left to the black line in the center is precisely equal to the distance between the black line in the center and the conditional association on the right. This blue line represents the version where the indicator variables were mean-centered rather than contrast-coded. It's like a weighted average of these two light blue lines. This blue line is somewhat closer to the conditional association for the dogs with straight fur because there are more dogs with straight fur in the sample. So it takes into account the difference in sample size between straight and curly when characterizing the main effect as the typical difference between no spots and spots. I could argue for either of these being the typical difference between no spots and spots. If I want typical to mean that any given dog is a 50-50 shot of being straight or curly, then I might use the black line. If I want typical to mean typical of the distribution of fur types in my sample, then I might want my simple effect to be somewhat more similar to the straight-furred dogs to take into account that I have more of them. We can also fit a regression model that does not have an interaction term. And you may recall from last week's videos that we can plot the results of a regression model like that as two parallel lines. These gray lines represent the slope of the curly variable in a regression model that adjusts for spots, but does not contain any interaction at all. And the distance between these gray lines represents the slope for spots from that same regression model. That's the difference between no spots and spots adjusting for fur type without an interaction present in the model. And you can see that the gray line passes very close to this point with 132 dogs in it, but is pretty far away from this point with only 36 dogs in it, because the point of a regression model like this is to minimize the sum of squared residuals, and so it's designed to come closest to the largest clusters of dogs. The distance between these two gray lines is the same as the height of this gray line that I've shown on the plot. I just situated it here to illustrate that this way of estimating a main effect results, in this case, in a main effect that is somewhat closer to the differential between no spots and spots among the curly-furred dogs. And the reason is that this kind of regression model, with two main effects and no interaction, takes into account all four sample sizes and realizes that we can't be quite as confident about the discrepancy for straight-furred dogs as we can about the discrepancy for curly-furred dogs, because this sample size of 36 for the straight-furred dogs with no spots is relatively small. The types of main effects will not always appear in this order. This blue one, remember, represents the conditional association when the indicator variables are centered. The black one represents contrast-coded, and the gray one represents a case where there's no interaction included in the model to estimate the main effect. And the gray one could fall between the black and the blue, or on the left of the blue line, depending on the discrepancies in sample sizes within each of the values of the moderating variable. The key difference between these three approaches is that the black line, the contrast-coded version, does not take into account any sample sizes at all. The dark blue line, the centered version, takes into account only the sample sizes of the comparison between straight and curly. And the gray line takes into account all four sample sizes. The gray line is the one that minimizes the sum of squared residuals under the constraint that we're not permitting an interaction in the model, that the lines have to be parallel. Note that these main effects are all the same if the cell sample sizes are all equal. That's why most stats classes don't make a big deal out of this. If you've designed a typical experiment, then your cell sizes will be close to equal anyway. But if they're not exactly equal, these three types of main effects can cause small discrepancies when you try one ANOVA function or another in R or SPSS or another software package, and it can be frustrating not to know why that's happening. This is the main reason I cover this material in this class.